Welcome. Let's look at another problem. Now this one, it may be in your notes and it's pretty much complete. So I didn't bother to erase it. We're just going to talk about this one, and then we'll do two on this video because this one was pretty much complete. All right, so consider the function 2x squared minus 7x plus 5. All right, so we see that it goes from 6 to 4. All right, so I added the extra value in because there has to be something that wasn't used, right? There has to be, if we're using the 4, there must have been a last right-hand value, right? Because every value but 1 is a left-hand value. The only one that's never used on a left-hand Riemann sum is the very last value because it's not the left hand of anything. It's the right-hand value of the last sum. Right, so here it's from 4 to 6, and the change in x is 1/10, which makes sense because you've got 20 values here, and so if you have 6 minus 4 divided by 20, well, that's going to be 2/20ths or 1/10, right? So that's why it definitely has to go from 4 to 6. All right, so we want the left edge of each of these. All right, so it's nice it's already plugged in because, well, these weren't the most fun. 20 value, plugging this in 20 times might take us a little while. So I don't mind this one being on the table. All right, so to find the sum, right, you take all of, and they've already multiplied here by the change in x, right? So if we were doing it and we only wanted to do it one time, we would have 1/10 times these values right there, right? The values of the function. So we'd have the area would be 1/10 times 9 plus 9.92 plus 10.88 and so forth, right? And then we just multiply it by 1/10 one time. That would make sense, right? Here, I guess they wanted to list everything out, or maybe they did it in an Excel sheet and it was already done. But they've already multiplied each value by the change in x. Right, so here we would have, if we were doing this, kind of the easier way, if we're not using a spreadsheet, we would have 1/10 times 400.4. And then when we multiplied by 1/10, then we'd get the 40.4 that they have right here for the Riemann sum, for the left Riemann sum. Right? So this one's already calculated out, and we're just interpreting it. Let's do one that's not all calculated out. And it is in a table. And we're going to do that right now. There we go. And let me read the question for you. Right, so the following table gives the dye concentration for a dye concentration cardiac output determination seconds after injection. The amount of dye injected into this patient was 5 milligrams. Use a left point Riemann sum to estimate the area under the dye concentration curve, and then estimate the patient's cardiac output in liters per minute by dividing by the amount of initial injection by this area. All right, let's do the Riemann sum part. All right, and then we'll answer this question. And although I don't know if my answer is in liters, I guess it's in liters per minute. I don't know. I think my answer might be, I had it calculated out earlier, and I think I actually have it in milligrams per minute. That's all right. No one's going to ask you to change units, so let's just go with milligrams. We're going to do milligrams per minute. We could do liters per minute, though. That would just mean moving a decimal point. Well, maybe we'll do milligrams. We'll do liters per minute. All right, so this is a left point Riemann sum. Right, so here's a rectangle, here's a rectangle, and so forth, right? Each one of these going from one value to the next is a rectangle. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, did I count them right? 11 rectangles, is that right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yes, 11 rectangles, right? And the last value is, all of these are the left, so this is the left, the first line I drew is the left-hand value for the first rectangle, and the second line I drew is the left-hand value for the second rectangle, and so forth. All right, and then so the last value doesn't get used, right, because that's on the right-hand side. All right, so it looks like it's 11 values here. All right, and we already know, and we don't have to really worry too much about figuring out the change in x, because they've already, we have the same change in x all over the place, right? So the change in x, you can see every one of these values is 2 apart. So that makes that pretty easy. I don't have to worry about subtracting and dividing and doing anything else. But we can see 24 minus 2 would give you 22, divided by 11 would give you 2. So change in x is definitely 2. All right, so the sum here, so our area, is going to be that change in x times, we're going to add up all of those values, right? And we're going to add up all, we're going to sum them all up, every one of those up, right? So the area is going to be 2 times, and then we'll add up all the left-hand sides. 0 plus 0.6 plus 1.4 plus 2.7 plus 3.7 plus 4.1 plus 3.8 plus 2.9 plus 1.7 plus 1.0 plus 0.5, and then we leave off the 0. Now, it's kind of interesting. The right-hand Riemann sum and the left-hand Riemann sum would be exactly the same. Oops, we're missing a decimal point there. I think it was probably there and it got lost in the 5. All right, so now we add those all up, which I smartly did beforehand, so I wouldn't have to do this while I'm taping. 44.8, all right? So we multiply those together, and that would be 89.7. No, 0.6. Oh, no, I'm sorry. Never mind. This value here, I already multiplied that. I already did this multiplying. So the sum is actually going to be 22.4 because I wrote down the final area when I was on my little cheat sheet on the board there, so I wouldn't have to keep adding them up for you on you having to wait for me. So 22.4 was the sum of those. The area would be 44.8. Right? So now we wanted to answer the question over here, this cardiac output. So now we're going to take, actually let's put it over here because it's kind of, so they told us how to figure it out, which is good because we probably wouldn't have known. So the cardiac output would be equal to, we take the 44.8, the area, and it said to divide it by the starting value. And it said we started off with 5 milligrams. So this would be our answer in milligrams, would be 8.961 milligrams per minute. And they did say liters, right? So there's 1,000 milligrams in a, you can tell me if I make a mistake, 8,961, so we'll just move the decimal point, and then we would have 8,000, oh, excuse me, the other way around. So we have to move that over. Let's just leave it, I don't mind making it bigger, but making it smaller, let's just leave it in this unit. Let's just pretend that it didn't say liters per minute, that it said milligrams per minute. So then we don't have to change it. But then we would just move the decimal place 4 places for liters. Right? So we'll just leave it like that. That's going to be the end of this video, and on the next video we'll do a few more where we're working with tables. Thanks for watching. Bye for now.